easier and easier to achieve these goals. But in practice, what's happening is it's actually getting harder. And I think there's a number of different reasons for why it's getting harder. One of the key ones, as we all know, is that the amount of data is growing rapidly, right? So the just the amount of data that's being collected, our ability to collect it. And so with so much data, it's harder and harder to do those things on the left. But not just that, it's also the demand for data that's increasing, because every company wants to be data driven, and everybody within the company wants access to the data. They want to be able to ask their own questions. They're not just expecting a report on their desk on Monday morning. They want access to the database. They want to run their own SQL queries. They want to build their own models, right? So you have a lot of demand for data. And then certainly the budgets or the size of the data teams, they're not growing at the rate that the data is growing or the demand for data is growing. And so you have this kind of complicated situation where basically you're trying to make this work, but it's actually very difficult. What we see happening in many organizations is you end up with this really complicated architecture, right? And so if you think about kind of data being collected in various different places, but a lot of data exhaust these days, especially in the cloud, kind of lands on systems like S3 and Azure storage and Google Cloud Storage, right? So basically blob storage. Think about things like log files and events that we're all collecting from different systems. And because it's traditionally been very difficult and slow to query the data directly there or to consume it directly from kind of cloud storage into some visualization or kind of machine learning application, what then often happens is that data gets ingested into some relational database, right? Typically a data warehouse. So in the cloud, this could be things like Redshift, Snowflake, Synapse, and so forth. Lots of different options there. But of course, those systems are expensive, and then it's a lot of work to maintain and create these data pipelines. And so you only do that with a subset of the data, right? You take some subset of what's landing in, say, S3 and load that into a data warehouse. And then often that's not enough, right? That doesn't really end there. You actually end up having to create extracts into the client tools. So if you're a BI user, maybe you're creating Tableau extracts, or if you're a data scientist, maybe you're downloading data into files on your laptop, so you can use a variety of Python utilities and libraries on those files with high speed. And then in addition to that, you often see additional copies of data being created within that data warehouse. So I was recently talking to a company that uses one of these cloud data warehouses, and they had almost 100,000 tables that had been created, kind of derived tables that they didn't really have any control over. They had no idea what was in them and whether they could even clean them up, because is somebody still going to use them? So you get all this complexity, all this really basically this mess, right? And the whole point of it is really just to make it so that that BI user or data scientist can query the data and get a really fast response time, right? To have kind of low latency. But when the stack is this complicated, these users here at the top, the BI users, the data scientists, they really can't do anything on their own, right? Because they're dependent on having access to the data and somebody to go wire up some new ETL as soon as they need something a little bit different. And then in addition to that, if you have so many different kind of silos and copies of data floating around, that means you really don't have a way to query the data across kind of all the data that the organization has, right? So you're constantly dealing with kind of very small and narrow scope of data, right? Maybe you're querying a specific cube, and that's fast, but you want to join that cube with what's in S3, and of course can't do something like that. So it ends up in many companies being weeks or months to respond to any kind of request to change something or add some new analysis or some new data. And that's very, very frustrating for the data engineering team. And it's also frustrating for the consumers of data, the data scientists and the BI users. And so a much better approach, right, would be if we could have a system that allowed us to query any data that we had in one of these cloud data lakes, and do that with the performance that the users here at the top require, right? So the BI dashboard, the low latency, high concurrency workloads, or the ad hoc work that a data scientist might need to do. And if we can enable this, right, if we can enable a scenario in which, or a platform in which all data can be queried and can be accelerated to the point where you don't have to build all that complexity to get fast response time. Then you can really change what's possible, right? You can go from weeks or months in terms of responding to a request for change to maybe being able to do that within minutes or hours at most. And then on top of that, you then have, as a BI user or a data scientist, you have full access to the data, right? Anything that you're allowed to see, you're able to see it. It's not a function anymore of, is it in the right system? Has it been ETL'd for me, and things like that. And what's making this possible really is this really fundamental shift in architecture. And this is something that shouldn't be surprising if you've been following kind of what's been going on in the application development world, where we've largely transitioned from a world in which applications were built as kind of monolithic stacks, right? Maybe taking ASP.NET on top of SQL Server, to now a world in which applications are built using things like microservices, where you have a number of or many different decoupled services, each running independently, being upgraded independently, and kind of monitored and scaled independently. And so the same thing, we see that happening now in the world of data infrastructure, and really enabled by kind of the public cloud. But if you think about even just 10 years ago, everything was about co-location of compute and storage. Whether you were looking at running Hadoop or you were using a data warehouse, you basically had a fixed set of hardware. We often call those a cluster. So you had a cluster of servers, and you would install both the storage as well as the compute on that same set of nodes. And there were good reasons for that. In particular, the networks were often the bottlenecks. So bringing the compute to the data provided a lot of performance advantages. But it created a lot of problems, right? And I spent years in kind of the early days of the Hadoop world. And there's a lot of complexity, right? Trying to run all these different open source projects, really that kind of zoo of projects on the same set of nodes, sharing the same memory and CPU resources, often created problems, right? A lot of conflicts and a lot of maintenance, and it was just very difficult to do. And then on top of that, the flexibility was an issue as well, right? You couldn't easily add more storage capacity without paying for more compute capacity, because you were adding increments of servers to the environment. What happened, I want to say about 5 years ago, 6 years ago, is as the public cloud was becoming more popular, you started to see this new architecture for kind of cloud data warehouses. And that was the separation of compute and storage, where instead of running the storage, kind of the file system, on the same set of nodes as the compute engines or the compute engine, you would actually separate those things, right? So data warehouses in the cloud will often use things like S3 behind the scenes to store their data, right? And therefore allow you to kind of scale the compute up and down, or provide a serverless model to query that data. The challenge, though, is that although this provides more flexibility and more efficiency, just from a kind of a scalability standpoint, it really doesn't fundamentally change what's possible, because in order to use that data warehouse, you still have to load the data into the system, right? So we all know that today, if you're using one of these cloud data warehouses, well, you're paying the data warehouse vendor to get the data in, you're paying them to query the data, you're paying them if you ever want to get the data out, and it becomes very, very difficult to use any other technology because you're basically in a position where you have to synchronize data across systems, right? If I want to use both say Snowflake and EMR or something else, right? I basically have to have the data in two different places. I can't have it in one place and process it fast. So that's a problem. Now, fortunately, what's happening, and you see a lot of the biggest companies, the biggest tech companies, and actually companies across all industries adopting this new architecture now, which some people call the cloud data lake or the Lakehouse, or kind of the open architecture. But really, the idea here is that the data is its own tier, right? It's independent of the compute engine. So what does that mean? Well, it means that the data is stored in open source file formats and increasingly table formats as well. And so we call this the separation of compute and data, not just compute and storage, right? So we're familiar probably with the file formats like Apache Parquet, which is a columnar format. Of course, there are kind of row-oriented formats like JSON and CSV and Avro as well. And then you have a variety of different engines. So, at Dremio, we focus on providing the best SQL engine for kind of the open architecture, but of course you have other engines that provide Spark, right? Companies like Databricks and machine learning engines like Dask, and really a long list of different technologies that you can use on the data if your data is stored in an open source format that's accessible to all these different engines. So what's really cool about this open data architecture is the flexibility that provides, right? You have at its core, you have the data stored in these open formats. And it used to be that data lakes were, basically just a bunch of files, right? You would store files, in for example, the Parquet format or the ORC format, and that was it. Maybe you had a little bit of metadata on top of that in like a Hive metastore. But increasingly, that's actually becoming more sophisticated, and we'll talk about that today. The tier of the data lake is including things like transactional table formats like Iceberg, created by Netflix, or Delta Lake, and then more advanced metastores. For example, we've been working on Project Nessie, which is a metastore that provides Git semantics for your data, where you can create branches and versions and so forth. Amazon provides Glue, which is another kind of cloud metastore. So by having the data stored in an open format, that allows you to, first of all, be able to use best of breed engines, right? So you can use a variety of different technologies to process the data. And there's typically kind of different engines that are good at different workloads or different use cases. And then it's not just what exists today, but also the ability to enjoy future innovation. Because many of the engines that exist today didn't exist 5 or 10 years ago. And in 5 years from now, there will be new technologies that you'll probably want to embrace. The second advantage here is no vendor lock-in, right? So the fact that the data is available to any of these engines means that it's very easy to complement your existing platform with technologies and also to replace your existing vendor. And so that is very different from the world of data warehouses. Historically, I'm sure many of you have heard horror stories about technologies like Teradata and Oracle. People trying to get off of those systems, and it becomes very, very difficult because you have your data stored in that system and a lot of processing happening 24/7 on that data. So being able to move that to another system and transition the workloads becomes something that's really impossible in many cases. And then the third thing is that this architecture is multi-cloud, and especially if you choose these engines at the top, those that run on different clouds, well, then you have an architecture that actually works regardless of what cloud you're using, right? And it becomes very easy also to move to a different cloud, or more importantly, as companies grow and acquire other companies or different groups within the company organically kind of start using a different cloud, you often end up in a situation where your company is using multiple different clouds for a variety of reasons. And so having the flexibility to use the same set of technologies makes it a lot easier. This is a quote here from Werner Vogels, who's the CTO of Amazon. And we work very closely with Amazon. And this is from a recent blog post where he said that with a data lake, data is stored in an open format, which makes it easier to work with different analytic services. And so this was about why Amazon internally uses this kind of architecture for their own internal analysis. It's something that we, as I mentioned, work closely with them on. So how do we enable BI workloads in this open data lake architecture, right? We've seen the advantages of that kind of flexibility, the ability to use different technologies, different engines. But in order to achieve really kind of a good experience for BI workloads, where it's not just about high throughput, but also about low latency and high concurrency, we need to look at new types of technology and innovations to make that possible. And so I'll talk about a few of them that we've kind of been very focused on or have been kind of emerging in the open source community, and then dive into them in a little bit more detail. So the first one here is having a semantic layer. And so if you think about traditionally, every BI tool would have its own semantic layer, and every user would kind of create their own virtual data sets or their own logical definitions of data and business logic. And that becomes a problem because you have then a situation where different users are seeing different definitions, different business logic. So what is a work week? Is that Monday through Sunday or Sunday through Saturday, right? You want everybody in the company to have the same definition, and also to be able to apply security consistently across everybody, regardless of what tool they're using. The second really important thing is having what I call BI level performance, right? It's not enough to be able to do a query with kind of decent throughput, but you really want to be able to achieve kind of low latency and high concurrency as well. And so a number of different things enable this. For example, being able to use the SSDs that are sitting on the engine itself to cache data, right? Because those SSDs are going to be closer to the compute than something like S3. And then in many cases, the amount of data in these environments is so big that scanning the entire data set to satisfy every query is going to be really inefficient, right? You're going to have to basically do a lot of the same work over and over again as people are accessing kind of the same dashboard or similar visualizations or doing similar analysis. And so providing technologies that or the ability to create kind of data structures that are more efficient for querying is advantageous here. And then there's this open source project that we've invested a lot in with many other folks in the community called Apache Arrow and Arrow Flight, which enable much faster processing and transfer of data. And I'll talk about that. Then one of the other challenges that comes up in these big kind of centralized environments is the ability to, or the need to, first of all, control kind of the cloud infrastructure costs, and then also to provide isolation between different workloads, right? So you want to avoid that noisy neighbor problem. And so we call that kind of a multi-engine architecture where you can have different engines, even with this within the same technology, automatically managed and automatically scaling to isolate workloads. And then finally, providing kind of a transactional data tier, right? If we think about the traditional data lakes or the early days of the data lakes, where it was basically just a set of files and companies had to kind of manage exactly how the data was stored and make sure that was efficient, and often made ingestion into kind of the data lake really complicated. There's a lot of innovation happening in this area to make that simpler, and I'll talk about that. So let's start with the transactional data tier and what are some of the more interesting things that are happening there. So there's a number of different projects here, much like there were different projects for kind of columnar file formats, right? We had things like Apache Parquet and we had ORC. And so similarly, there are a few different projects that are kind of trying to enable this transactional data tier. And two of the ones that we see and are promising are Apache Iceberg and Delta Lake. Iceberg is interesting because it's backed by a significant community of companies. So it was created by Netflix, and with a lot of investment from other companies like Apple and Expedia and Adobe and Alibaba and LinkedIn and many others. And so there's a lot of investment happening from kind of the community in this project. And some of the advantages of or the benefits that you get by using Apache Iceberg are the ability to have kind of cloud data warehouse semantics, right? So it's not just kind of a read-only system anymore. You can actually do data mutations with DML. So SQL commands like insert and update and delete, right? So you can do these types of operations and delete a single record or update a single record in a data set when it's stored in this format. The other benefit here is that you have transactions, right? The ability to do multiple operations and kind of commit them atomically. So that's another benefit of using something like Apache Iceberg. Time travel, the ability to kind of query a previous snapshot of a data set. So if you have a table, basically every change to that table is kind of the differences are basically stored in the system using something called a manifest file, or kind of a manifest list that points to manifest files, which then point to the data files. And so that allows the different engines to query the data and process previous versions of the data. And then also you have a much easier solution now for evolving schemas and partitions without having to rewrite your data or your queries. So as the data set evolves, and maybe you want to add columns or change data types, or change how you're partitioning the data. Maybe you want to partition instead of by month. Now you have so much data that you want to change to partitioning by day. You actually don't have to rewrite the entire data set, and you can just make that partition definition change, and everything keeps working, right? And new data can be loaded into kind of the new partition structure. So this really gives you kind of that flexibility that you in the past could only get with a database or a data warehouse. You now have that in the data lake itself. And then the additional benefit of something like Apache Iceberg is that it enhances the performance and scalability and reliability of the system as well. And there's a number of different things or a number of things with Iceberg that are different from, just using, say, Hive Metastore or Glue to store your metadata. And I'll talk about a few of them, but there are actually many others. So I encourage you to go to the Iceberg website and kind of read more if you're interested. But the metadata is stored in the file system itself, in the distributed file system, in S3 and ADLS. It's not stored in the metastore anymore. So the metastore becomes just a pointer to the kind of the manifest list file, which is kind of the root file for the data set. But the detailed metadata, all the schema information, all the files that are that make up that data set, all of that is now stored in the object storage, right, in S3. The other thing is that you no longer need to scan or cache large directories to plan a query. So in the past, when you were using kind of the let's call it the Gen 1 metastores, the system would actually have to scan the entire directory to know which files make up a data set. And oftentimes, if you had data sets that were made of tens of thousands or hundreds of thousands of files, that would be very, very slow, right? You would have really bad performance. And we tried to overcome some of that with kind of caching metadata, but that wasn't a perfect solution either, right? Because updating the cache would take a long time. So by using something like Iceberg, we no longer have to read the directory to know what files are in a data set. That's all stored inside of these manifest files. And in fact, the information within these manifest files actually allows us to prune the data files or even entire partitions based on column statistics. So we know, for example, the minimum and maximum value of a specific column in each data file. So we don't have to open that file to even understand that. That's all stored in these manifest files. And everything is done as kind of immutable snapshots in S3, right? So Iceberg is designed to provide serializable isolation and reliable reads. And so every new update to the data set is kind of a new version of that data set. And when you're reading a data set, for example, as part of a query, you're reading a specific version, right? There's no issue with concurrent writers that are writing new versions of this data set while you're reading it. You're going to read a very specific version and get a consistent answer. So that's Iceberg. But Iceberg is focused on, and Delta Lake as well are focused on kind of that on the single table, right? And there's always a metastore that basically provides kind of the catalog of all the tables that you have inside of the data lake. And so we call that, you can think of that as the metastore. And the metastore could be very, very simple. It could be just, here's the names of the tables and pointers to the manifest list of each of these tables. But we looked at, how can we modernize the metastore in kind of the data lake? And we created this project called Nessie, which you could think of it as kind of a much more cloud native metastore versus kind of the Gen 1 metastores. And we also took an approach here that not only provides a catalog that points to all the tables, but also adds additional kind of more sophisticated functionality that provides a Git experience for the data lake. So what this means basically is kind of two key benefits. One is the ability to create branches and query data within specific branches, right? And previous points in time. So for example, if you wanted to reproduce a model that you had created a month ago, you could, when you created that model, you can just create a tag the way you do in Git. And then at any time, if you wanted to query the data based on that tag, you can query it and you'll get a consistent view of your entire data lake based on that tag, right? So in this example here, I'm using the main branch and I'm selecting from table T1 so that the main branch would be the one that I'm selecting from. but I could select star from T1 within the ETL branch. So I could use this syntax, and then I'm selecting a table from a specific branch, in this case, the ETL branch. Or I could select a table from a specific point in time, or even within a branch at a specific point in time. And this has a lot of benefits. You can, things like compliance, right? I can go and see who are all the people that have changed this data set and what are all the changes that have happened. I can compare a data set across 2 different versions, right? I can, if I wanted to say, look at why did we make a specific decision a month ago, I can run my dashboard on last month's data, that kind of thing. That will be possible. And this is still an early stage kind of open source project. It's not quite ready for production, but you can read more about it, and this will work across all engines. It's an open source technology. And then the second benefit of Nessie is that it provides multi-table and multi-engine transactions, and it does that through branches. So in the example below here, you can see we're creating a branch called ETL. We're running a number of Spark jobs in this branch, and then updating some reflections. That's a Dremio technology to accelerate queries. And then we're merging that back into the main branch, right? So by creating a branch and being able to use different engines within that branch, you basically have the ability to then kind of roll that back in or merge that back in an atomic operation. And so that simplifies a lot of use cases. It allows data scientists to experiment on the data, for example, without impacting the current live view of the data for other use cases, and makes it also very easy to kind of support various data promotion workflows where you go from dev to staging to production, as an example. So that's some of the innovation that's happening in that data tier. And I want to talk about a little bit about things that are happening now in kind of the execution layer, and how do we make these queries run faster. And one key thing that's happened there over the last few years is the rise of Apache Arrow as an industry standard for representing data in memory. And this is actually an open source project that we created at Dremio, or co-created at Dremio, very early on, where we realized that there wasn't a kind of a common way in which databases were representing data in memory, and basically every database was doing it its own way, and there wasn't something kind of equivalent to, say, Parquet, but for memory. And so we open sourced our internal memory format. We worked with the Python community and Ursa Labs to do that. And long story short, Arrow is now downloaded over 20 million times a month and used by most data scientists. And so you can see the graph here. This is actually not even the latest data, but it's been growing very, very rapidly. And what Arrow then enables is the rise of kind of different technologies to process that data very fast. And so because it's stored in memory in a columnar format, you can leverage vectorization, for example, in the CPU to process an array of values in parallel. And so we've created a project called Gandiva, a kind of a sub-project of the Apache Arrow project, which basically uses LLVM, which is a compiler technology, to compile expressions, parts of a SQL query, into kind of native code that is highly optimized for kind of the existing CPU to run in efficiently. And so that's Gandiva. And then we're also now taking advantage of the fact that so many systems and data scientists are using Arrow to create something called Arrow Flight, which is an RPC layer built on top of Apache Arrow. So basically what Arrow Flight does is allows 2 different systems to exchange data in the Arrow format, and does it with gRPC over HTTP2. But that's much, much faster, for example, than something like ODBC and JDBC, or kind of a REST API, because it supports parallelism. It's very highly kind of compressed and compact compared to kind of traditional RPC systems. So that's kind of the raw execution, but we also wanted to make sure that we were being efficient in terms of I/O, right? Because in order to achieve the performance that people need for BI workloads, you have to be able to get really low latency and be very efficient in terms of use of resources. And so we created something called C3, a columnar cloud cache. And the idea here was to provide NVMe level performance, or I/O, even when accessing remote storage like S3 and ADLS. And the way we do that is through a cache, right? So basically, every Amazon instance these days, or every Azure instance, right, comes with local SSD, often NVMe. And it's ephemeral, right? So it goes away when the instance goes down. But as you're running queries, you can leverage this cache to basically not have to go back to S3 and read the same data multiple times, right? And so that's what we do with these NVMEs that are part of the EC2 instances or the virtual machines on Azure. And the really cool thing about this is that it's transparent to the people that are using the system, right? So in fact, you can use the engine, not even know that the data is getting cached, because objects are immutable. It doesn't, you're never getting any stale data, for example. And then it's also saving you money because there's costs associated with going to S3 and doing kind of gets and puts, right? There's a price to that. And so that could be significant as well, depending on the workload. So this is how we speed up the I/O. But there's ultimately going to be use cases where the amount of data is so large that getting kind of that interactive response time, that maybe sub-second response time, is still very difficult unless the data can be structured more efficiently, right? And we've seen this in other domains, indexes and cubes, and there's a lot of history around being able to leverage more efficient data structures to support faster queries, right? And often that is something that is needed. So we created something called data reflections, and the idea was basically to allow you to have kind of more optimized representations of data without requiring the user, whether it's an analyst or a data scientist, to be aware of these data structures, right? So historically, if you think about cubes and extracts and aggregation tables in like a data warehouse, the user typically has to choose the representation that they're going to use, right? They're connecting to a specific cube or to an extract, or they're connecting to a specific summarized table within the warehouse so they can get faster performance. But that means that anytime you want to make changes to these data structures and optimize things, you have to change every client application, every dashboard, and it just becomes very, very difficult to manage like that. And then it's also makes it very inflexible to the user, because let's say they connected to a table that has all the events pre-aggregated by user, and then they want to drill down into the events of a specific user. Well, that's not available in that table that they're connected to, right? So they have to go to a different table for that use case. And so what we've done is we've created this data reflections technology where the query optimizer automatically figures out how to use these different representations of data. So the user is not aware of them. They're kind of operating in the logical world and just querying kind of tables and views. But behind the scenes, if we recognize an opportunity to leverage kind of a pre-aggregated version of the data, or a pre-sorted version of the data, then we can do that to make the query faster without requiring the user or the dashboard or whatever tool they're using to be aware of these different representations of data. So that provides kind of the speed of query. But we also want to make sure that we're being very efficient in terms of the use of hardware, and in the cloud, that's EC2 instances primarily, or Azure virtual machines or Google instances as well. And then we also want to make sure that we don't suffer from kind of noisy neighbor issues where one workload is impacting the performance of a different workload. And so the way we approach this is by basically supporting multiple engines. So if you were to, for example, deploy Dremio's AWS edition, then you would notice that you can define multiple engines, like say an extra large engine for your maybe your batch queries, and a large engine for your marketing dashboards, and a medium-sized engine for your executive BI dashboards or something like that. And then you can define rules that decide basically or help determine which engine a query is going to run on. So, if a query comes in, you could leverage information such as who they are, what time of day it is, and so forth, to decide which engine to use. And the system will automatically start and stop that engine based on whether there's anything running on it. So, reduces costs and also ensures that different workloads and don't impact each other. Right, the data science kind of more ad hoc workload doesn't impact the production, BI dashboards, as an example. And then finally, in terms of just kind of from a logical data standpoint, we wanted to really integrate kind of a semantic layer into the platform itself, so that you don't have this kind of data sprawl and different semantic layers being created for each tool that people use. And so the typical scenario, in the past would look something like this. You'd have, your data lake or data warehouse with the tables in it, and in every client application, whether it's your Tableau dashboards or your Jupyter notebooks or whatever tools you were using, Power BI, you would define your own kind of calculated fields and your own data sets in any of these tools. And what that caused was this kind of very siloed proprietary kind of semantic layer for each application, right, and for each group. And what we believe is the right approach is to have kind of a shared semantic layer within the data platform itself, so that you can define security policies and you can define kind of the right definitions of data, and then have them work consistently across any application, so that you can start thinking of these different tools as thin clients, rather than having the business logic defined in the kind of the client application itself. Of course, one of the things that makes this possible is having kind of this data reflection technology I talked about earlier, which allows us to accelerate those queries in a way that's transparent to this user. So the user could connect to this shared semantic layer, and they can still get that sub-second response time because of the data reflections, right? And so they're happy to use kind of more of a thin client approach because of that performance enhancement. So let me jump in and show you what this actually looks like in practice, and I'll share I'm going to share my desktop so we can actually use a BI tool here. All right, so I'm going to open up just a simple kind of demo environment here. What you'll see here on the bottom left, so what we're looking at is the Dremio engine, which is a SQL engine for data lakes. Now, in a second, I'm going to jump into a BI tool, and I'm on a Mac, so I'll use Tableau, which runs on Macs, but you could use whatever BI tool to do this. So just quick orientation here. We're connected to a number of different data lake sources. That's just because this is a demo cluster, so we're connected to our Glue data catalog, some of our S3 buckets, some Azure data lake sources, and so forth. So this is you would typically just connect to whatever kind of data lake, either kind of the raw file system or a metastore. And then you can just kind of browse the directories and start querying data if you want. You have the semantic layer, which we just talked about. That's kind of organized in spaces. So let's create a space called AI Camp, and I'm going to set the permissions just to leave it open. But of course, you can control permissions and use role-based access control. So AI Camp, you see there's nothing in it right now. Also, every user has their own personal space in the semantic layer, so they can create their own virtual data sets. These are these green ones, and then also upload like spreadsheets. Those are the purple ones if you wanted to join that with what's in your data lake. So let's start with a very simple example. Oh, and I should also mention that if you have external sources like relational databases, you can also connect to those as well. And that gives you an opportunity to join like small data sets in a relational database with the big data that you have in the lake. So to use just to show you kind of the speed that you can get from a BI standpoint. So I have this data set here that we use for a lot of demos of New York City taxi trips. And there's over 1 billion records in this data set. So you can see here, there's a vendor ID, a pickup time, the drop-off date and time, the number of passengers, the trip distance in miles, a bunch of things like that. So I'm going to open this up. I click on the Tableau button, opens up in Tableau on my laptop. We just make that really easy. This is you can also start from, in this case, Tableau, and just connect to Dremio like you would to any database. Give it a second here, and what I'm doing here is I'm creating a live connection from the BI tool to the Dremio environment, right? So there's no data being exported or anything like that. So let's look at just the number of records that we have here. So I'm just going to drag the count, and you can see we have 1.025 billion records in this data set. Let's aggregate it by time. So let's drag the pickup time here, and you can see there's 160 million records, 170 million records per year. You can kind of see it went up and down a little bit. If I wanted to look at it not by year, by week number, you see number of trips, taxi trips in New York per week. Let's look at something more interesting like the tip amount, right? So I'm going to drag the tip amount here, and change that from a sum to an average. So I want to see what's the average tip amount in New York. And interestingly, you can see that the average tip has been going up, or this data set was 2009 to 2014. Actually, I need to update that more recent data. But you can see that it actually seemed to have increased pretty linearly, and it's not clear what exactly the reason was. Maybe the overall rates went up, so the tip went up, or maybe the default on the screen, went up for the tip amount. But we can investigate. We can look at the total amount, right, and see if there's kind of any correlation there. So it looks like the total amount went up. You can see the spike here. This spike here probably is explained by this increase in rates in general. But generally, the rate at which the total taxi trip amounts was increasing is much lower than the tips. So something else was going on in terms of causing tips to go up. But what you can notice here is we just ran over 10 different queries, and all of them completed very, very fast, even though we have over 1 billion records in our data lake, right? So I'm going to open up the jobs tab here, so you can actually see the different queries that were coming in, right? The last one here being, this is Tableau is constructing these queries, so we're just accepting them from the BI tool, and so you can see the average tip amount, the average total amount, some math on the date to get that day of week, or the week number, right? And then you can see kind of the amount of time it took, so less than 1 second. And the flame means that it was accelerated because of one of these data reflections. Okay, so you can see that we can get this kind of sub-second response time directly on the lake or the Lakehouse. Let's look now at another example where we create a virtual data set. So what I'm going to do is I'm going to take this trip distance in miles and translate it to kilometers, which is just multiplying roughly by 1.6. And so I'm creating a new calculated field, basically. But all I'm doing is everything is SQL. Everything is ANSI SQL in the system. So I'm multiplying the miles by 1.6 and aliasing it as trip distance in kilometers. So what I'll go and do is save this inside of the AI camp space that we created earlier and call this trips kilometer, right? Trips KM. And now if I go back to my my BI tool, right, then to the data source tab, what I'll do is I'll look for the AI camp space. That's basically a schema now. And instead of that original data set, I'm going to drag the new trips KM, this new virtual data set. And so if I go back here, I can now see that I have this trip distance kilometer field, and I can query that from any client application. So in this case, I'm using this BI tool, but this could be a Jupyter Notebook or any data science application. So you can see the average trip distance in kilometers, right? And it's just as fast, even though that's a calculated field. And then maybe one last example here before we wrap up. I'll join this with something that's outside of the data lake just to show you what that looks like. So if I click on the join button, we actually recommend things you might want to join it with based on the behavior of other users. But of course, you can, again, just do everything in SQL, which is what most people do. So this is doing an inner join with this data set of weather data in New York, right? And the weather data is in a Postgres database. So I'll save this in the AI camp space and call this the, let's call this trip weather. So now I have a new data set called aicamp.tripweather. And so you can just refer to any data set in the system in Dremio as a dot separated kind of path, right? So in this case, aicamp.tripweather. And by the way, you can see the kind of, it's a join between this data set in kind of Postgres and this one in the data lake. So if I go back to my BI tool now, still in the AI camp space, you can see there's a new data set called trips weather, and that's a join across 2 different systems. So if I drag that here, you can see now that I actually should have removed all this analysis here first, because it's not relevant to this data set now. So you can see now that I have, for example, the temperature information, like the maximum temperature and like the trip distance in kilometers. And so I have kind of basically columns coming from multiple sources, right? So if I look at trip, let's see if this will work. The maximum temperature, actually I want this to be a dimension, right? And maybe I want to look at the see the trip distance. I probably should have changed that to be discrete. But this now allows me to run queries that kind of span multiple data sources, and you can actually see the queries that are running here. So you can see the ones that I canceled are the ones with this. But this query is going to be slower now because data is having to get pulled from another source, from a relational database, which isn't going to be as fast, right? So. All right. So with that, I am going to stop sharing here and open this up for questions. Okay, so we had a bunch of questions, I think, in the chat. Let's see. Okay, one question was, all data can be queried is not necessary. A good thing is data quality is very important. And that's true. That absolutely, you don't necessarily want all data to be accessible to everybody. And so you when using kind of a data lake architecture or a data warehouse, actually, it's important to make sure that you're only exposing the data that you want to expose to your users. I think that's true for really for any system. It's not so much a function of the architecture and data lake versus data warehouse. It's you got to make sure the data quality is there, and unfortunately, I don't think there's a magic way to do that, right? That's kind of just kind of part of working with data, right? Do you have more info on Nessie and any prerequisite to run it? Sure. Actually, you can go to the Nessie website. So it's projectnessie.org, and there's documentation, and you can actually get instructions on how to run it. It's pretty cool. Like I said, it's early days, but something we're very excited about, and I know many others are as well, to have this kind of Git experience on your data.
By the way, just a quick comment. For the last week, we have a tech talk on the project Nessie. So if you want to know more about that, you can watch the recordings. I will post the link to the previous event too. And I also quickly remind everyone, you can ask questions in the chat. And if you prefer, you can raise your hand to speak to ask questions too. Please go ahead.
There was a question here, where did you pull data from in the first use case when it was fast? So the data in my example was actually on ADLS, so on which is the Azure equivalent of like S3. So you're going to have much better performance if your data is sitting on like an object store and it's in a columnar format than if it's in like a relational database. There's another question, if in your opinion, is the star schema dead, and if so, why? And no, I don't think. I think the star schema is a logical model that's actually very useful, right? I think we, when we think about how data is stored, we don't want to, like, there's a reason. There are many advantages to having data kind of normalized versus denormalized. So I don't think it's dead at all. What I do think is important is that do you really need to be first of all, do you really need to be joining the data live for every query? So imagine you have a star schema and you have hundreds or thousands of people that are going to be running different kinds of queries on that star schema, on that, on that big join, right? So do you want to be physically processing that 20-way join for every single query in every single dashboard? Or do you want to, for example, have that, that join cached, right? So that queries are going against that cache, right? And so that's one of the things you get with data reflections. But there's other things in the engine itself to make star schemas go fast. For example, sometimes when you have a star schema, you have like a where, in the where clause, you might have like a filter on one of the dimension tables, right? So like let's say you have, users and then a cities table, right? Where do they live? And somebody might do a filter not on the city ID, but on the city name. And so you want to make sure that the system can figure out that there is a filter happening on the dimension table at runtime, and then apply that to prune and not have to read all the fact table, all the information that's for other cities. And so that's something called dynamic filtering or adaptive filtering. It's something actually we've spent a lot of time on in the engine itself. And then how do you recommend getting started or practicing at home with this data stack? So there's a lot of ways to kind of use the, practice with this kind of open architecture. If you wanted to try out Dremio, then you can actually, in the Amazon Marketplace, there's a free version of it, so you can actually spin it up, and it's actually should only be a few minutes to get going. But yeah, there's a lot of information out there about kind of data lakes and how to get started. So yeah, I think that was the last question, which brings us to.
I have another question that's actually come to me. By the way, just remind everyone, if you post the questions, make sure to select to everyone, so we can see the messages. So the question is, there are a lot of solutions on data lakes, like from AWS, from Google, and also from startups, open sourced. What's your recommendations or kind of like general guidelines to use them?
Yeah, I think that's a good point. Actually, that's part of the value, part of the idea, right? Is that you can have the same data stored in open formats and used by a variety of engines. What we see a lot is, with our customers, is that a lot of them will use, Dremio for like the SQL-based workloads, so things like BI, and then use like Databricks for, like the data processing or machine learning. So that's a very common kind of combination that we see. But there's many other options, right? You can use like Amazon EMR, for example, for Spark workloads as well, and so there's all sorts of options out there. You mentioned that we should use a columnar format. That means I would need to denormalize it from MySQL and don't use joins. No, the columnar format is just like the way the file, kind of the structure, the physical structure of the data, right? So you can still have a star schema in your data and still have the data normalized. But when you columnarize it, it's just the difference between like, say, a CSV file where, if you think about the bytes in a CSV file, you have all the values of row number 1, and then all the values of row number 2, and then all the values of row number 3, versus a columnar format like Parquet, you have the values of column 1 stored, followed by the values of column 2, followed by the values of column 4, for let's say in groups of like 10,000 or 1,000 records, and that gives the engine the opportunity to basically ignore not have to read the data that is not being requested. And so it's very common in tables to have like, you have 500 columns, but the query only needs like 10 columns. So a columnar format means that the engine doesn't have to read the other 490 columns in the data set. What do you do when data comes from different countries and have compliance rules? Again, that's one of those things where there's no magic solution, right? If you have to keep the data in a different region, then you should run kind of a separate environment, one in Europe and one in the US, right? And not mix that data. I think there's a lot of gray area here too, in terms of companies that can that internally have processes to kind of get approval to move specific data sets, because what you don't want to be doing is you don't really want to be doing, live joins across 2 different geos, certainly not at scale, right? Because A is going to be slow, right, because of the latency, and then B, you might have very high kind of egress costs from the cloud provider. So you just got to be careful when you're moving large volumes of data across regions.